Hello friends, welcome to my channel SN Physics. In my previous video, I have discussed about the action of a transistor. In this video, I will discuss about the circuit for drawing characteristics of transistor in C configuration and will explain nature of these characteristics. Let us see, this is the transistor. Actual transistor. This is the emitter. There is a notch here. The leg near to the notch is emitter. There is a washer. There is another washer that prevents the legs from contact with the body of the transistor, whereas collector is connected to the body, so there is no washer. So this is emitter. This is base and this is collector. The symbol of NPN transistor, emitter, base, collector. This is NPN transistor, this number is CL100, and arrow in the emitter in the outward direction is the symbol of NPN transistor. So we are discussing here NPN transistor. This is the NPN transistor. Now this is the circuit for drawing the characteristics in C configuration of the transistor. Transistor in the active region, if it is in the active region, what is the active region? Before going to the different regions, this is the block diagram, three-dimensional block diagram of the transistor. This is emitter, this is base, this is collector. These red balls are electrons, white balls are holes. In N-type semiconductor, majority carriers are electrons, so the number of electrons is large in comparison to the number of holes. Whereas in base, which is P, number of holes is much greater than the number of electrons. And it is again N-type, so red balls number of electrons is much greater than the number of holes, white balls. These blue balls are the donor ions, or here it is acceptor ions. So this is already discussed in my previous video. I am not going to details of all these things. This is another block diagram. This is emitter closest to the notch. This is base. This is collector. In between my fingers, this is the collector. This is the collector. Now, when emitter is forward biased, and collector is reverse biased, it is in the active region. So first of all, we are discussing active region. When the transistor is in active region, the transistor is in active region, that is emitter is forward bias, emitter being N, connected to the negative of the battery, and it is connected to ground. Collector is reverse biased, it is N, so it is connected to the positive. So as it is connected to the negative of the battery, this negative terminal repels all these electrons in this direction, and current is in this direction. Emitter current is outward direction, so the arrow is in the outward direction. So this is the direction of current. This arrow indicates the direction of emitter current. Now, as it is in the active region, so emitter should be forward biased, that is connected to the ground or negative terminal, and base, emitter base junction should be forward biased, this is P, so it is connected to the positive of the battery. Voltmeter is connected in parallel to this, so positive is connected to the positive terminal of the battery and negative is connected to the negative terminal of the battery. Current is flowing in this direction, so this is plus, this is minus of the microammeter. Base current is very poor, so it is measured in microammeter. Again, collector is reverse biased. This is NPN. N is connected to the reverse bias, so it is connected to the positive terminal of the battery. As it is connected to the positive terminal of the battery, so current is flowing in this direction. These electrons are collected by this positive terminal, so current is in this direction, inward. So this current is in this direction, so positive terminal of the milliammeter is in this direction and this is minus, so collector current is in this direction. So this is the basic circuit diagram to measure the voltage between collector and emitter. Another voltmeter is connected to the parallel of the battery circuit, positive to the positive and negative terminal is connected to the negative. As these two negatives come in this position, so it is grounded here. This is a circuit diagram. I hope circuit diagram is clear to you. Now let us draw the characteristics. This is the characteristics. When the transistor in active region, in this region, so negative terminal repels all these electrons in this direction. A few electron and hole recombine here, giving rise to a small base current. Let us suppose initially the base current is, say, IB is equal to 20 microampere, say, and it is fixed. So if we increase VCE, what will happen? When this voltage VCE is increased, more electron will reach collector and collector current will increase linearly with base current. So as IC equal to beta IB, so collector current increases with increase in base current. If base current is increased, suppose it is IB is equal to 40 microampere, so at any VC, as base current increases, collector current increases. Say it is IB equal to 100 microampere, then collector current is at a particular VCE, say particular VCE is this. At this particular VCE, collector current, this is the collector current, this collector current say IC1 and this collector current say IC2. So IC2 is greater than IC1, as because we know IC nearly equal to beta IB. So as IB increases, IC increases. As IB increases from 20 microampere to 40 microampere, IC1 and IC2, say this is IC2, this is IC1, so IC2 is greater than IC1. But this region is linear. It is almost straight portion. This, if a transistor is to be used as an amplifier with minimum distortion, its operation should be restricted to the active region. So this active region is preferred for distortionless operation of the transistor as an amplifier. Now, there is slight increase in the, for a particular base current, there is a slight increase in IC with VC. Why it is so? As collector base junction is reverse biased, this is positive, N is connected to the positive, so this junction is reverse biased. Increase in VC, if this voltage is increased, the width of the depletion layer will increase. As a result, if the depletion layer is increased, base width will decrease. This decrease of base width with increase in VCE is called early effect. Due to this early effect, beta increases significantly, and as beta increases, IC will increase. So with VCE, IC increases significantly. There is a definite steep rise, there is a slope, and from this slope we can find out this is IC2 minus IC1 and this is IB2 minus IB1. So we can find out from these characteristics very easily. Beta is equal to IC2 minus IC1. Say it is IC2, this is IC1, this is IC2. This IC2 is for IB 40 microampere, say IB2, and IB1 20 microampere minus IB1. So from the knowledge of IB1 and IB2 and corresponding IC2 and IC1, we can find out beta, and for cell 100 it is almost 200 to 400. For BC107 also, it is also almost 400. It is a very large value and it is a temperature dependent, however. So this is all about the active region. Now, as IC, this is the parameter of the output circuit, and VCE is also the parameter of the output circuit. So these characteristics is called output characteristics. This is called output characteristics. The IC, this IC is measured in milliampere and VC in volts. So both the parameters are of output, so it is called output characteristics. This is the input part. We know this is the input part of the transistor, this is the output part of the transistor. So input parameter IB is fixed here for a particular IB. For a particular IB, we are drawing VCE versus IC, and this is the curve. So output characteristics is for active region, it is clear. If we increase further VC, this potential barrier breaks down and a sharp rise in current, this is called breakdown region, sharp rise in current is found of the IC. So breakdown occurs. So we cannot increase VC very much. It will create breakdown of the collector base junction. Okay. If now base collector junction, that is collector is reverse biased. Emitter is forward biased. Emitter is forward biased as before, but collector base junction is also forward biased. Emitter base junction forward biased as well as collector base junction is also forward biased. Emitter being N connected to the negative of the battery. This positive comes to this point, so it is grounded. So this potential is practically zero. So it is zero. But base is connected to the positive, so it is being P side connected to the positive. So base emitter junction is forward biased. Base emitter junction is forward biased. And collector base junction N being connected with the negative, now collector base junction is also forward bias. This condition is called saturation. So now the transistor is in saturation. There is battery direction is reversed. Here battery positive, the positive of the battery is connected to the collector. Now negative of the battery is connected to the collector. So direction of the battery is reversed. So VCE, this voltage, this VCE voltage is now negative. With respect to 0, this VCE is now negative. So the characteristics, this is the origin 0 and it is negative, this is positive. Now VC is negative. As soon as collector is negative, collector is forward biased, this negative terminal will repel all these electrons. So although base emitter junction is forward biased, electrons are coming in this direction, electrons are pushed to the collector, but these electrons are repelled by the negative terminal of the battery and current ceases to flow. This is the nature of the graph. Current ceases to flow and goes to 0. So collector currents almost become 0. If base current is high, so it will go to the 0. This also go to the 0. So as the collector junction is forward biased, there is negative, it will repel electrons and current stops ultimately. IC is almost independent of IB. This region, they merge together. So these regions are almost same for all the IBs. So IC is almost independent of IB near this 0 IC. This is called saturation region, which is indicated by this blue box with blue dots. An active region is the green region with green dots. Green boxes, this region is active region, and blue box with small blue boxes inside it is the saturation region. Now, if both emitter and collector both are reverse bias, if this is called saturation region. On the other hand, if emitter base junction is reverse bias as well as collector base junction is also reverse bias, if it is reverse bias, no electron will flow from emitter to base. So this is cutoff region. Transistor will go to this shaded region is called cutoff region. So if emitter and collector both are in reverse bias condition, the transistor stops to flow and it is called in the cutoff region. So this is all about the output characteristics. Now if we plot input parameters, that is base current with base emitter input voltage, what will be the nature? Look, this is base emitter junction. It is nothing but a diode and it is forward bias. So the nature will be just like the characteristics of a diode. Suppose initially VCE is 0 voltage, that is VCE is absent, so it is nothing but a diode. So this is the characteristics of a diode. We are plotting VB along x-axis and IB in microampere in y-axis. So this is a exponential rise which I have discussed in my video on diode. This is the nature of the curve. If now VC is increased slightly from 0 volt to 1 volt, then collector will collect more electrons more rapidly. So exponential rise will remain in the exponential fashion, but the rise is more rapid. If we increase VC more to 2 volt, so the nature of the graph will be this. So this is the input characteristics, as because both parameters voltage and currents are of input side of the transistor. Another characteristics which is not so very important, but I am discussing this. Suppose one parameter is of input and another parameter is of output, then it will be a straight line graph. This is say IB in microampere in x-axis and IC collector current in milliampere in y-axis. Then the nature will be almost linear, as because IC is equal to beta IB, neglecting the small reverse current. So this is called mutual characteristics. As because one parameter is of input and another parameter is of output, so it is mutual or transfer characteristics. Name is there. This is transfer characteristics. So the name is mutual characteristics or transfer characteristics. The effect of IB is transferred to the output IC. So all these are the characteristics of a transistor in CE configuration. Look, this emitter is common. So it is common emitter configuration. I think it is clear to all of you. Thank you.